Hi, today we're going to talk about the G protein coupled receptor, or GPCR, and how it enables cell signaling. First, let's set the stage for this discussion. At the moment, we have the star of the show, GPCR, here. It is currently bound to a G protein. The G protein is currently inactive as it is attached to GDP. Over here is the protein adenylyl cyclase. We'll see why this protein is important soon. Finally, in the extracellular matrix, we have a ligand. This ligand will bind to GPCR and cause a conformational change in the protein. This conformational change causes GDP to detach from the G protein. Then, GTP attaches to the G protein, activating it. The G protein then makes its way to adenylyl cyclase and activates it. Adenylyl cyclase then converts ATP into cyclic AMP. Cyclic AMP is a type of secondary messenger, and its job is to magnify the signal that the ligand induces. Think about it this way. If the G protein were to be the only messenger of the signal, it would only activate one iteration of the target protein. However, since there are multiple secondary messengers, they can activate multiple iterations of the target protein. But how does cyclic AMP activate the target protein? Well, it initiates a phosphorylation cascade. Here's how it works. First, the cyclic AMP binds to and activates the first kinase protein in the cascade. Kinases are proteins that phosphorylate or add phosphates to other proteins and activates them. So, this kinase will use up an ATP molecule and activate the second kinase. Then, this kinase will use another ATP molecule to activate a third kinase. Finally, the third kinase will use yet another ATP molecule to activate the target protein. The protein will then initiate a cellular response to the signal. For example, the protein could be an enzyme that catalyzes a reaction when active and creates a product. Keep in mind, since there are multiple secondary messengers, there are multiple phosphorylation cascades going on at the same time. This means that there are multiple cellular responses to the one ligand, meaning that there would be multiple products created instead of just one, based on my previous example. There's one more critical step in the signal transduction pathway, and that's turning the phosphorylation cascade off. In order to deactivate the phosphorylation cascade, cells use protein phosphatases. The protein phosphatases remove the added phosphate from an active kinase. This process forces the kinase back into its inactive form. This reaction happens for every kinase in the cascade, turning the cascade off and ending the signal. That's all there is to it. Thank you for watching.